In mathematics, mixing is an abstract concept originating from physics. The attempt to describe the irreversible thermodynamic process of mixing in the everyday world. Mixing paint, mixing drinks, etc. The concept appears in ergodic theory, the study of stochastic processes and measure-preserving dynamical systems. Several different definitions for mixing exist, including strong mixing, weak mixing and topological mixing, with the last not requiring a measure to be defined. Some of the different definitions of mixing can be arranged in a hierarchical order, thus, strong mixing implies weak mixing. Furthermore, weak mixing implies ergodicity. That is, every system that is weakly mixing is also ergodic. Mixing in stochastic processes. Let be a sequence of random variables. Such a sequence is naturally endowed with a topology, the product topology. The open sets of this topology are called cylinder sets. These cylinder sets generate a sigma algebra, the Borel sigma algebra. It is the smallest sigma algebra that contains the topology. Define a function, called the strong mixing coefficient, as in this definition. P is the probability measure on the sigma algebra. The symbol, with denotes a subalgebra of the sigma algebra. It is the set of cylinder sets that are specified between times A and B, given specific, fixed values, etc., of the random variable, at times, etc. Then it may be thought of as the sigma algebra generated by the process's strong mixing ifs. One way to describe this is that strong mixing implies that for any two possible states of the system, when given a sufficient amount of time between the two states, the occurrence of the states is independent. Types of mixing. Suppose xt is a stationary Markov process with stationary distribution Q. Denote L squared the space of Borel measurable functions that are square integrable with respect to measure Q. Also let t equals e, x0 equals x, denote the conditional expectation operator on L squared. Finally, let z equals L squared, dq equals 0, denote the space of square integrable functions with mean 0. The row mixing coefficients of the process xt of the process is called row mixing if these coefficients converge to 0 as t infinity, and row mixing with exponential decay rate if rho t less than e minus delta t for some delta greater than 0. For a stationary Markov process, the coefficients rho t may either decay at an exponential rate, or be always equal to 1. The alpha mixing coefficients of the process xt of the process is called alpha mixing if these coefficients converge to 0 as t infinity. It is alpha mixing with exponential decay rate if alpha t less than gamma e minus delta t for some delta greater than 0, and it is alpha mixing with sub-exponential decay rate if alpha t less than xi for some non-increasing function xi satisfying t minus 1 lane xi 0 as t infinity. The alpha mixing coefficients are always smaller than the row mixing ones. Alpha t rho t, therefore if the process is row mixing, it will necessarily be alpha mixing too. However, when rho t equals 1, the process may still be alpha mixing, with sub-exponential decay rate. The beta mixing coefficients are given by the process is called beta mixing if these coefficients converge to 0 as t infinity. It is beta mixing with exponential decay rate if beta t less than gamma e minus delta t for some delta greater than 0, and it is beta mixing with sub-exponential decay rate if beta t xi 0 as t infinity for some non-increasing function xi satisfying t minus 1 lane xi 0 as t infinity. A strictly stationary Markov process is beta mixing if and only if it is an aperiodic recurrent Harris chain. The beta mixing coefficients are always bigger than the alpha mixing ones, so if a process is beta mixing it will also be alpha mixing. There is no direct relationship between beta mixing and row mixing. Neither of them implies the other. Mixing in dynamical systems. A similar definition can be given using the vocabulary of measure-preserving dynamical systems. let be a dynamical system, with T being the time evolution or shift operator. The system is said to be strong mixing if, for any, 1 has. For shifts parametrized by a continuous variable instead of a discrete integer n, the same definition applies, with replaced by with g being the continuous time parameter. To understand the above definition physically, consider a shaker full of an incompressible liquid, which consists of 20% wine and 80% water. If is the region originally occupied by the wine, then, for any part of the shaker, the percentage of wine in after repetitions of the act of stirring is in such a situation. One would expect that after the liquid is sufficiently stirred, square integrable eigenfunctions with associated eigenvalue of 1. In general, a shift operator will have a continuous spectrum, and thus will always have eigenfunctions that are generalized functions. However, for the system to be weak mixing, none of the eigenfunctions with associated eigenvalue of 1 can be square integrable. Formulation: the properties of ergodicity, weak mixing and strong mixing of a measure-preserving dynamical system can also be characterized by the average of observables. By von Neumann's ergodic theorem, ergodicity of a dynamical system is equivalent to the property that, for any function, the sequence converges strongly and in the sense of Cesaro2, i.e., a dynamical system is weakly mixing if, for any functions, and a dynamical system is strongly mixing if, for any function, the sequence converges weakly to, i.e., for any function. Since the system is assumed to be measure-preserving, this last line is equivalent to saying that, so that the random variables and become orthogonal as grows. Actually, since this works for any function, one can informally see mixing as the property that the random variables and become independent as grows. Products of dynamical systems. Given two-measured dynamical system in, one can construct a dynamical system on the Cartesian product by defining. We then have the following characterizations of weak mixing. Proposition: our dynamical system is weakly mixing if and only if, for any ergodic dynamical system, the system is also ergodic. Proposition: our dynamical system is weakly mixing if and only if is also ergodic. If this is the case, then is also weakly mixing. Generalizations: the definition given above is sometimes called strong 2 mixing, to distinguish it from higher orders of mixing. A strong 3 mixing system may be defined as a system for which holds for all measurable sets A, B, C. We can define strong K mixing similarly. A system which is strong K mixing for all K equals 2, 3, 4, is called mixing of all orders. It is unknown whether strong 2 mixing implies strong 3 mixing. It is known that strong M mixing implies ergodicity. Examples are rational rotations of the circle, and more generally irreducible translations on a torus, are ergodic but neither strongly nor weakly mixing with respect to the Lebesgue game measure. Many map considered as chaotic are strongly mixing for some well-chosen invariant measure, including the dyadic map, Arnold's cat map, horseshoe maps, Kolmogorov automorphisms, the geodesic flow on the unit tangent bundle of compact surfaces of negative curvature. Topological mixing. A form of mixing may be defined without appeal to a measure, only using the topology of the system. A continuous map is said to be topologically transitive if, for every pair of non-empty open sets, there exists an integer n such that where is the nth iterative f. In the operative theory, a topologically transitive bounded linear operator is usually called hypercyclic operator. A related idea is expressed by the wandering set lemma. If X is a complete metric space with no isolated point, then F is topologically transitive if and only if there exists a hypercyclic point, that is, a point X such that its orbit is dense in X. A system is said to be topologically mixing if, given open sets and there exists an integer n, such that, for all 1 has, for a continuous time system, is replaced by the flow, with G being the continuous parameter, with the requirement that a non-empty intersection hold for all. A weak topological mixing is one that has no non-constant continuous eigenfunctions of the shift operator. Topological mixing neither implies, nor is implied by either weak or strong mixing. There are examples of systems that are weak mixing but not topologically mixing, and examples that are topologically mixing but not strong mixing.